Good morning, everyone. I'm Marcus Batista. Today I'll be presenting the findings of a project we are working on at the University of Miami titled Occurrence and Evolution of New Particle Formation Events over the Remote Southeast Atlantic. The process of new particle formation involves the formation of thermodynamically stable clusters from trace gas molecules and their growth to larger sizes. On the superior panel, we see an example of banana curve where we observe the growth of particles from 1 nanometer to larger sizes. The newly formed particles can grow through mechanisms of vapor condensation and coagulation, depending on the availability of condensing vapors and if they can survive the scavenging by pre-existing aerosols. As particles they grow, they can be activated into cloud levels when they reach the Hopper minimum, and they can further contribute to CCN population and further influence regional climate. So understanding the formation and evolution of atmospheric aerosols and their properties is essential in predicting their impact on Earth climate. Compared to NPF studies over the continent, direct observation of NPF events over the remote oceans are still relatively insufficient despite the large coverage of ocean on the planet. Over the remote ocean, NPF is more likely initiated by sulfuric acid and methane sulfonic acid, produced from the oxidation of the methyl sulfide, which is produced by plankton in oceans. In the remote oceans, NPF events have been commonly observed in the free troposphere, which is a major source of marine CCN, and it apparently occurs especially near the outflow of convective clouds, where it can be created conditions promoting the NPF events. Recent study found that NPF event can occur during the stratospheric air intrusion, facilitating the oxidation of DMS and the formation of new particles. The newly formed particles in the free troposphere, they can be transported downward by large-scale subsidence and further entrained down and transporting the newly formed particles from free troposphere to the boundary layer. NPF within the marine boundary layer is considered to be unlikely due to the relatively high surface area of the sea spray aerosols, which act as condensation and coagulation sinks of nucleating vapors and also for newly formed particles. However, recent studies over the eastern northern Atlantic show that NPF events can occur regularly in the upper boundary layer during the post-cold frontal conditions, due to low concentration of pre-existing aerosols, lower temperature, relative abundance of precursors, and higher actinic fluxes. Particles formation depend on high actinic fluxes to facilitate photochemical reactions. An open cell structure of clouds, also called as packet of clouds, showed here in the picture, can allow sunlight penetration, leading to the oxidation of sulfuric compounds and the formation of new particles. However, although we see that cloud system can play a role in creating conditions favoring new particle formation, it is unclear if this mechanism also applies to other marine atmospheres. For that, we examined the occurrence and evolution of new particle formation events over the Southeast Atlantic Ocean, especially around the Ascension Island, which is a volcanic island located 3,000 kilometers west from the Southeast Africa. The Southeast Africa provides approximately 30% of the world biomass burning aerosols, and the Ascension Island atmosphere is influenced by the biomass burning in the continental Africa advected westward, especially during the months of June to October. However, depending on the wind patterns, the Southeast Atlantic can experience a relatively clean environment from the months of November to May. So the measurements at Ascension Island represent the remote Southeast Atlantic environment where the air mass requires at least 5 to 6 days to arrive from Africa. In this work, we examined the occurrence and the meteorological conditions associated with new particle formation events and predicted their contribution to CCN during these events. We analyzed aerosol properties, trace gas concentration, vertical velocities from different altitudes, and meteorological data collected by the AAAR mobile facility at Ascension Island during the layered Atlantic smoke interaction with clouds, the LASIK campaign. The LASIK measurements were at surface level and spanned from June 1st, 2016 to October 31st, 2017. And to understand the vertical distribution and transport of aerosols, complementary data were obtained from research flights during the Cloud Aerosol Radiation Interaction Enforcing Clarify campaign. The Clarify campaign was conducted parallel to the LASIK campaign and correlated to the ground measurement at Ascension Island. This figure shows an example of NPF event observed at Ascension Island on September 12, 2016 from 7 UTC, which is the same as local time, to 1 a.m. on September 13, 2016. On panel B, we observed the nucleation mode aerosol with a geometric mean size ranging from 15 to 25 nanometer and at an approximate growth rate of 1.55 nanometer per hour. We see that there is a growth, but no complete banana curve was observed in this event. And in fact, none of the NPF events observed at Ascension Island contain a continuous growth from 10 nanometer to larger sizes, suggesting that NPF is unlikely near the surface of the island. This is most likely due to the relatively high concentration of pre-existing aerosols from continuous generation of sea spray and the impact of African biomass burning aerosols entrained from the free troposphere. We also noticed that from 8 to 11:30, we see that the nucleation mode aerosol dominated the total number concentration, with a fraction of the newly formed particles reaching approximately 90%. At the same time, we see the increase in concentration in the size range of from 3 to 10 nanometer, indicating that these aerosols were recently formed. At 7 UTC, we see that the average carbon monoxide mixation and the refractory black carbon were relatively lower than the monthly average concentrations. But we see that we still have concentrations of black carbon, and the high surface area suggests that the surface atmosphere at Ascension Island is unlikely to promote new particle formation directly. The appearance of nucleation mode aerosols also corresponds to the downward motion observed in the boundary layer at different altitudes below the cloud base. Also, we see the decrease in surface area correlating to a moment of precipitation due to the removal of pre-existing particles. So these observations suggest that the nucleation mode aerosols are likely transported vertically through the downward motion above the Ascension Island. Here we examine the seasonal variation of newly formed particles, CO, RBC, and absorption coefficient measured at Ascension Island. The results show that N below 30 is statistically higher from June to September 2016 and from July to October 2017 compared to the period of October to June 2017. Interestingly, this period corresponds to the times where Ascension Island is influenced by the long-range transport of African biomass burning plumes. The lower RBC and the absorption coefficient during the NPF event indicates that the NPF event required a clear environment, although some NPF events also have considerably higher RBC and absorption coefficient, especially in 2017. Recent studies showed that the ultra-clean and the smoke boundary layer occur frequently at the same season, and it happened because during the ultra-clean, it corresponds to the period of more intense and frequent precipitation, as well as stronger diesel production and coalescence scavenging from the deeper boundary layer, which effectively removes the pre-existing aerosols but not the non-soluble gases such as CO and potential precursors of new particle formation. Dimethyl disulfide was found in the biomass burning plumes, and they can found to contribute to the formation of sulfuric acid, and um, also in collaboration with highly oxidized molecules, they can contribute to new particle formation. The reduction of pre-existing aerosol due to precipitation can promote new particle formation, which is demonstrated in this figure. Panel A shows a positive correlation between monthly average N below 30 and monthly cumulative precipitation. Also, we see the months where we have the higher N below 30 generally have the lower ambient temperature, in agreement with observation that lower temperature can stabilize newly formed particles. On panel B, we see that there is a negative correlation between the surface area and the monthly cumulative precipitation, and this can be explained by continuous entrainment of biomass burning aerosols from free troposphere to boundary layer, and also by the continuous generation of sea spray aerosols that contribute to the concentration of aerosol surface area. And the fact that there is no strong correlation between the N below 30 and the surface area at Ascension Island again suggests that these newly formed particles are likely transported. On panel C, we see that when the fraction of newly formed particles is above 0.4, there is a stronger air downward velocity between 200 and 700 meters above the Ascension Island. That indicates that there is a vertical transport of particles from the upper boundary layer to the surface. Our observation of new particle formation events at Ascension Island generally agree with those found during the Clarify campaign. Here is the flight we observed indication of new particle formation on September 5th, 2017, conducted at around 200 kilometers southeast of Ascension Island. We see by the potential temperature, CO, and ozone profile that there is a well-defined boundary layer structure with a boundary layer height at around 1,800, with a clear separation between those two layers, demonstrating that there is a limited air exchange between them. Also, if we notice between the 1,000 and 1,800 meters, there is a substantial decrease in accumulation mode aerosols due to the coalescence scavenging at the cloud level, where you can see here indicated by the liquid water content. Meanwhile, at this altitude, the concentration of total aerosol is much higher than the accumulation mode aerosol near the top of the boundary layer, and also is substantially higher than the concentration near the ocean surface. This phenomenon suggests that new particle formation produce additional aerosols in the upper boundary layer. Also, we can see that on the same day at Ascension Island, we noticed that there was a nucleation mode aerosol with a size of 17 nanometers emerging at around 1035 UTC that continuously grew to 40 nanometers, demonstrating that the new particle formation can be transported and observed near the surface of the boundary layer. Based on the growth of NPF events identified at Ascension Island, we further predicted the contribution of NPF events to CCN population, considering the loss due to scavenging by pre-existing aerosols. We identified the Hubble minimum of 74 nanometer and an average growth rate of 0.57 nanometer per hour, indicating a relatively slow growth. However, given that any new particle formation occurs during the ultra-clean environment, we found that significant fraction of the newly formed particles can still grow and contribute to the cloud formation. However, we should note that the frequency of new particle formation over the Southeast Atlantic is relatively low, and the contribution of newly formed particles to total aerosol concentration is also relatively low. So comparing NPF and other aerosol processes, the entrainment of aerosol from free troposphere, especially from biomass burning events, is more likely to contribute to most CCN over the Southeast Atlantic. In this study, we investigated the occurrence and evolution of NPF events over the remote Southeast Atlantic using ground and airborne observations. We found that NPF events over the remote Southeast Atlantic primarily occurred during the biomass burning season and impacted by the African biomass burning aerosols, especially from June to October. The pre-existing aerosol concentration and the surface area concentration were low, which was likely due to more frequent precipitation as well as stronger diesel production and coalescence scavenging. However, the relatively high CO mixation and moderate black carbon concentration suggest that the transport biomass burning plumes may contribute to the occurrence of NPF events. Using the vertical velocity retrieved from the Doppler lidar as well as airborne measurements of ultrafine aerosols, we found that the newly formed particles observed at Ascension Island are associated with the vertical transport from upper boundary layer, where the wet removal of pre-existing aerosol is most frequent and efficient. Our model suggested that a considerable fraction of the newly formed particles can grow to sizes above the Hubble minimum and further contribute to the CCN. Our work shows that NPF could occur regularly over the remote Southeast Atlantic, even during periods when the marine boundary layer is influenced by the biomass burning plumes. So I would like to acknowledge all the members of my group, the CAST, Center of Aerosols at the University of Miami, and the funding from the Department of Energy, and the support from the Aerosol System Research. Thank you very much.